here as an equation. This is what it would look like. I noticed nobody tried to make an equation. Sometimes I have kids that like go to an equation for that, like they are doing an example. But if you want, d over dx means that you are taking a derivative, right? So if you're taking a derivative of x to n power, then you multiply out front by that n, and you subtract 1 from the n that was your exponent, right? So that's a way that we could write this as like an equation for that. So we should be experts at this by now because we practically were Isaac Newton coming up with calculus just now. You guys figured it out. I didn't even have to teach you how to do it. So a little bit of notation though. When you take a derivative, you want to make sure that you label it as the derivative, which you're going to do by calling it f prime of x, like that. So when you take a derivative, you're going to label it f prime of x. Chandler, what will we get for the first example? 3x squared. And so like for number 2, I'm going to call it g prime of x. Make sure you don't just write an answer. You want to write g prime of x. It's very important that it's labeled as the derivative. Michaela, what do I get for my answer on that one? 20x to the 4th. So you guys see what I'm saying? Like we could, if the kid knows how to multiply and subtract, we could go show them how to do this, right? Like you could teach a 4th grader how to do this. It wouldn't even be that hard for them, probably. At least, especially if we don't go into some like negative exponents or anything like that. There are some properties of derivatives that tell us the constant rule is that the derivative of c is just going to be 0, where c is any real number. We talked about how that really is just the same rule, right? We could really just use the same rule for that, but our book does have it listed out as a separate rule because it probably is helpful for kids to see that. Scalar multiples, we were really already doing. A scalar multiple is a number multiplied by an expression. If you are taking the derivative of a number multiplied by expression, you just multiply that number out. So like whenever we took the derivative of x to the 3rd, there was nothing written out here. There was no scalar multiple, right? That 4 right there is really the scalar multiple. Like what we're doing mathematically could be written like this: 4 times 5x to the 4th. There is no need to write that step there. But if we're just taking the derivative of the x to the 5th, we'd get 5x to the 4th, and then we would multiply it by that scalar multiple to get 20 right there. So that rule is sort of almost inherently, you just do it there. And we've already really used sum and difference rule because on some of these problems, like we had here, we had 3x to the 1st plus 2x to the 0 power. We just did each piece separately, right? We did our rule for each piece. And that's what your sum and difference rule tells you, is that if things are separated out by a plus or minus sign, you just take the derivative of them separately. So we have really already been applying all of these properties there. So just to make sure we've really got it, let's see for 3. For this, Zach, what would I get for number 3? Beautiful there. And for number 4, Alyssa, what would I get for that one? 45. Beautiful. Okay, now 5 and 6 are a little bit different. Because does our rule say anything about fractions or anything about roots? It does not. But there's some things we already know about fractions and roots that we can turn it into something that we can deal with. What could I do with a fraction that has a variable in the denominator. I could rewrite this as x to the negative fifth. Now that is not taking a derivative. That's just rewriting it. So with negative exponents, they're like bad children. You lock them in the basement, right? But if it's already in the basement, you can move it back up to the top and make it negative again, all right? So I could write that with a negative exponent. And so this is still the original function. When I take the derivative, I can just use the rule now. Some of these are going to say y equals instead of f of x equals. So you've got a couple options with how you do this as far as notation goes. The easiest one is just to do y prime there. And then you will have negative 5x to the, what's my exponent? Negative 6. A lot of times I want to put negative 4, but you're doing negative 5 minus 1 is negative 6. So there. You could leave the answer like this. A lot of times they will send that variable back down to the bottom, so negative 5 over x to the 6th power. Only the x goes to the bottom because there's no parentheses or anything here. That negative 6 only applies to the x. Yeah, it would be fine to leave it. Definitely on a free response, just leave it. Don't worry about it. A lot of times on multiple choice, they'll make it look like this. Okay, so if you have fractions, you could change them to negative exponents. What about a root? Okay, I could change this to x to the 1/3 power. And so if you were like, I have no idea why she just did that, you need to remember your rules for roots. So like if I have the b root of x to the a power, that is going to be x to the a over b. The whatever is your root goes on the bottom of the fraction because roots are on the bottom of a tree. And this one doesn't have an exponent on the inside, but if there is no exponent on the inside, it is a 1. All right. So again, this is not our answer. That's just changing this so that we can deal with it. Because if we don't change this to just a regular x to a power, we don't know how to take the derivative of it. So we are going to do k. K prime of x, and we're going to multiply out front by our exponent. So we got 1/3 x to the, now you're going to get better and better at fractions in your head, hopefully, but you're doing 1/3 minus 1. You must have common denominators for that. So that is 1/3 minus 3 over 3, right? Which will give you negative 2/3. So you're going to get x to the negative 2/3 power. Definitely do that in your head if you can, but if fractions sort of still throw you for a loop, write it over to the side. There. Now, they might leave it like this, and they might not. We've got a negative exponent now. What could we do? We could send it to the bottom. In this case, since this is already a fraction, think of it like this, right? You got 1/3 times x to the negative 2/3. So it would look like this. You're going to have that 3 is in the bottom, and the x to the 2/3 would be with it. That is x to the 2/3, not x times 2/3. And then they might even change it to a root. So if they change it to a root, the 3 is out here, and it would be the cube root of x squared. So it might be any of those 3 options right there as the answer choice. And honestly, AP does not have a standard way of putting the answer. They may throw any of those on a multiple choice question. So you just need to know they're all equivalent there. Okay, questions? All right, let's look at a couple more just tricky things that you might run in. Actually, no, this isn't tricky. Sometimes you are asked to find slope of a graph at a specific point. So we used to would have had to do, let's just imagine what we used to have to do. Like in the olden days, back last week, we would have had to do the limit as x approaches 1 of f of 1, or f of x minus f of 1 over x minus 1. You don't necessarily have to write this down, but we would have to do all this, right? And then that would look like this, limit as x approaches 1 of, let's see, we'd have 3x to the third minus 4x squared. And I believe we're going to get a negative 1 there, all over x minus 1. And then we'd have to work all of that out, right? Which I'm not going to go any further with. Now, all we need to do is we need to take the derivative, right? Which is a very simple derivative here. So, Lucas, what's the derivative of this function going to be? Very good. 9x squared minus 8x. So if we want the slope of a graph at that point, all we've got to do is plug in that number. You want to make sure you label this. So you would say f prime of 1, and then you just plug it in. So 9 times 1 squared minus 8 times 1 is going to give us 9 minus 8. So we just get 1 for our answer there. And if I want to do this for 0, I would just do f prime of 0. And so that'd be 9 times 0 squared minus 8 times 0. That's just going to give me 0 for my answer. And if I want to find f prime of negative 2, which I have 9 times negative 2 squared minus 8 times negative 2. And that would be 9 times 4 plus 16, so 36 plus 16 is going to give us 52 for our answer. So much easier, right? So much easier. All right, so this is going to make tangent line problems much easier. So some of the stuff you're going to see on that FRQ, it's going to be tangent line stuff. You don't have to do limit definition of a derivative anymore. You still, for a tangent line, need a point, you need a slope, and you need an equation. For your point, you're finding f of 1. This part doesn't change at all. It was already very straightforward. F of 1 is 1 over 1 squared, which is just 1. So 1, 1 is your point of tangency for this tangent line. Okay. For a slope, we're looking for f prime of 1, which is what we've already done. It's so much easier now, though. Now, this particular problem, what have I got to do to it before I can take the derivative? Move it up, so we got x to the negative 2. So if I want to take the derivative of this, f prime of x is going to be negative 2x to the negative 3. Now, I would suggest in this case, it is going to be easier if you go ahead and make this negative 2 over x to the third, because you got to plug numbers into this, and it's just easier to do if it doesn't have negative exponents in it. So, if I'm finding f prime of 1, that means I'm going to have negative 2 over 1 cubed, which is just negative 2. There's my slope. There. And now I just need to write my equation, which is going to be y equals slope of negative 2. Point is 1, 1, so x minus 1 plus 1. There's my answer. So that those tangent line problems, they still say point, slope, and equation, but it's so much easier because you don't have to do limit definition of a derivative for that. Okay, questions there? Okay. All right, so let's look at this. This is an application of these, we used to, in math, when I taught math 1, we would always do the pumpkin chunking. I actually need to check with Coach Swisher and see when they're shooting off their bottle rockets. Because we might could go out there and take some calculations. And I know he's got a second period because Hunter's in there. So we might. But if you shoot something into the air, it is going to follow a quadratic curve based on gravity. So a pumpkin is launched from a height of 15 feet with an initial upward velocity of 60 feet per second. So this equation right here gives the height of the pumpkin t seconds after it was launched. You'll notice that the initial height is this number added over here to the end. You may also notice that the initial upward velocity is the number next to your t. That's always the case. And then that negative 16 t squared is always the same because that comes from your acceleration due to gravity right there. So we could do this for lots of different situations, but they've given us this particular situation. So A says what was the average velocity of the pumpkin from 0 to 1 seconds. Now what do we do when we see, well, first of all, we know what to do for average rate of change, right? Average rate of change, what should we do for that? Y2 minus Y1 over X2 minus X1, slope formula, right? Whenever I see average velocity, that's going to be the rate of change of height, because if I have time here and height here, and I do slope, that's my change in height over my change in time. Height is a distance, right? So it's change in distance over change in time. That's velocity for that. So average velocity is your average rate of change right here. And we just have to do slope. So I would find h of 0, which would just be negative 16 times 0 squared plus 60 times 0 plus 15. That's just going to give you 15. So that point is 0, 15. And then I'm going to find h of 1, which is going to be negative 16 times 1 squared plus 60 times 1 plus 15. So let's say it's going to be 75 minus 16. We get 59 there. Yeah, 59. So I got 159. And so if I want to know average rate of change, I would do 59 minus 15 over 1 minus 0. So that is going to give me 44 over 1, which is just 44. And that would be feet per second. All right, so for average rate of change, you're finding slope between the endpoints. So you get to get those endpoints, you plug in those values, and you just do slope formula. Average rate of change is not a calculus problem, right? We could have done that long ago. But the second part of this is going to ask you for the instantaneous velocity of the pumpkin at t equals 1. So instantaneous velocity is the slope of the graph at that point. And how do we find the slope of a graph at a point? What? That would be an estimate. We don't want to estimate. We want to know exactly what it is. So if I have a graph and I want to know the slope of the tangent line of that graph, what do I have to find? It's just the derivative, right? Derivative. So when you see instantaneous velocity, again, knowing right here that velocity is your rate of change of the function that we're starting with, right? Instantaneous velocity is the derivative of that height right there. So that velocity, like your v of t, if you want to call it that, is really just h prime of t. So your velocity is your instantaneous rate of change. So we can take the derivative. So if we take the derivative, the function was 16t squared plus 60t plus 15 right there. What? Oh, I think I messed that up then. It should have been positive. So our first answer's wrong, and the question's wrong. Oh no, it was positive. Oh, the 16. No, never mind. 16 is negative. 16 is negative. I was thinking you said 60. Yeah. Okay. So 16 is negative. So if we take the derivative, we get negative 32t plus 60. So if I want to know the velocity of the function, I just got to plug in 1 to this. So v of 1 is going to be negative 32 times 1 plus 60. So negative 32 plus 60 is going to give me 28 feet per second. Now, that's slower than our average rate of change from 0 to 1. Why would that be? What's going to happen to a pumpkin as you shoot it into the air and it goes up? It is eventually going to fall back down. And so if it's going to fall back down, it's got to go up, it's got to stop, and it's got to start going back down, right? So as it's going up, it's slowing down, right? So it's slowing up as it goes down because gravity's pulling against it. It slows down, so it makes sense for that average rate of change from 0 to 1 to be higher because it was going faster at the beginning than the instantaneous rate of change at 1. Now, it's positive, which tells me it's still going up. If I went over a little further, if I plugged in 2 for this, I'd start to get a negative. That velocity has direction. It tells you it's going back down if you get a negative velocity. Speaking of, my question for C, this is something you might want to know. So perhaps you get hit by this pumpkin, right? We might want to know how fast that pumpkin was going whenever it hit you, right? So if you want to know the velocity of the pumpkin when it hit the ground, if you are unfortunately standing where the pumpkin is going to land and you get smashed by this pumpkin here, we might be interested in how fast that pumpkin was going whenever it hit you. For this, what would I have to find? I know I want velocity, so that's the derivative, right? But what do I need to know? I need to know how long it was before it hit the ground. So to know how long it was before it hit the ground, I need to think about that height function, right? What's the height of the pumpkin when it hits the ground? It's 0, right? So I'm going to just use Desmos on this. I don't think they're going to give you one where you can't because I made this one so you could technically do it, but we're about out of time. So most of the time in real world data, you wouldn't be able to do this by hand anyway. You could use quadratic formula, but no need in making it more difficult than it needs to be. So I'm going to make this higher so we can see what's. So like right here, our pumpkin goes up, it comes back down. It's going to hit the ground right here. Right? So that's our height of our pumpkin. It hits the ground. Actually, no, this is not a by hand problem. You could do it with quadratic formula, but you couldn't do it by hand because we're getting 3.98524. Right? That's the time when it hits the ground. So for my derivative, it was, I'm going to call it, I'm just going to call it y, or d, t right here. It was negative 32 t plus 60. And if I plug in right there, negative 32 times that number plus 60, I get negative 67.527. Let me also show you something pretty cool here that Desmos will do. Desmos can take a derivative for you if you're plugging in a point, right? So if I type h prime of t, it doesn't want to do anything. But if I tell it h prime of that number we just found, it will automatically give it to me, and I don't even have to find it by hand. Although it's not very difficult to find this one by hand, so it's not saving you much. But so we got negative 67.528 there. Wrong thing. And if this were a calculator active problem, the only thing you would have to write is V of 3 point, oh gosh, what was that number? 985. If that's off a little bit, don't worry about it too much. That's all you would have to write if it were a calculator active problem. What we're doing is we are doing negative 32 times 3.985 plus 60. And we are getting feet per second here. So if you were hit by this pumpkin, it would be going negative 67.528. Negative meaning it's coming back down. Right. Okay, questions? All right, so your assignment is from the textbook. There's a lot of problems there, but they should be very fast. You do not have to copy the problem. You should, for most of these, you should just have like a string of answers, right? They should be very fast for you to do for those.